Hello, my name is Craig Willis, and I'm a doctoral student at the University of Illinois. I work for National Center for Supercomputing Applications at the University of Illinois with the National Data Service, which is a whole lot of stuff. And I'm going to talk about our pilot project, which covers a lot of the same territory on expansion models for biomedical data search. So, as I said, I'm a doctoral student focused on experimental IR, but I'm also a research programmer with NDS and NCSA. And for our projects, Elasticsearch is actually a core technology often for data search. So this was a very compelling project, I think, from the NDS side. We see this test collection as a really unique IR research data set. I don't think there's anything else like this out there right now. And for anybody involved with the RDA Discovery Paradigms group, there's discussion around potentially offering environments to repurpose this to enable more evaluation. And I work for the NDS Labs group, so that's another positive outcome of participation. So I think a lot of this has already been covered. So we know that searching for biomedical information requires specialized language, and we know that users don't choose the best query terms. And in general, tried and true method, automatic query expansion, has proven effective in a lot of domains. And so the question was, how effective is this within the context of the BioCaddy test collection? And since the data set descriptions tend to be pretty sparse, what if we expand using an external collection? So I think the Emory group covered this as well, and we focus on PubMed in particular. So our query expansion is similar to the one just presented, but differs from the query expansion that's currently in DataMed. So this is blind feedback or pseudo-relevance feedback. And the only point I'll make on this, so in the original query, search engines tend to make the assumption that query terms are all equal. So we have no additional information, everything gets a uniform weight. So in addition to expanding the query, most query expansion methods will give you additional term weighting, and it brings as the query closer to what the document collection is and gives maybe a little more explicit weight to important terms. And so the basic process, I think, has been covered here. Given the original query, we take the top ranked documents, you calculate term weights based on those top documents, and you now use that expanded query to reissue against the collection. And generally in traditional ad hoc IR, we treat this as either unigram models or we don't pay a lot of attention to structure, whereas I think obviously DataMed is very concerned with structure. And there are a variety of different techniques here within the probabilistic framework, the language modeling framework. We have something called relevance models. We have Rokio expansion, which I think is often used in the vector space paradigm. So again, we looked at external expansion. So usually with feedback expansion models, you expand using the primary collection. But when it has sparse data or short documents, you can turn to external collections. And so DataMed, PubMed's open access collection seems like a natural extension. You can also use general collections like Wikipedia. And we will report those results in our progress report, but not here, just in the interest of time. We did look at Wikipedia as well. So the good and the bad of expansion. So overall, tried and true methods have demonstrated to actually improve effectiveness generally. It may provide better query terms and a natural way of weighting query terms. The bad is that it's computationally more expensive than you're just issuing the original query. Bad queries tend to perform worse, and we have the classic effectiveness trade-off, which is even if we go through this process, do the users really notice a difference? So it might be statistically significant, but no one will notice. Just to place where our work is, and this fits, I think, a few slides that have already been shown here. We take the index for granted. We're not paying attention to structure. We just take the raw BioCaddy challenge data, and we're focused on the retrieval model itself. And when you're looking at retrieval models, obviously you have a lot of choices. We have multiple different, but two primary different kind of theoretical frameworks that you can work in, from language modeling, probabilistic models, to vector space models. We have the addition of expansion models. Within each of these, there are different retrieval models that have different criteria, different benefits. And since we were doing this in kind of an exhaustive evaluation, we compared a lot of these. I'll just report kind of the main ones. So our pilot tasks were really three major steps. We wanted to go back to the BioCaddy challenge data, do a systematic evaluation of kind of the two probably most popular expansion models, including external collections like PubMed and Wikipedia, and then really sit down and think about what's the best expansion approach for DataMed considering the constraints. You're working with Elasticsearch, which is based on Lucene. So performance is one thing, but how easy is it to integrate? And then we actually implemented a prototype expansion module intended for use with DataMed. So a note here, so we work primarily with a tool called Indri, which comes out of CMU, and it's a research search engine and framework that's really designed for experimental evaluation. It's based around probabilistic retrieval models, and so the primary retrieval models come from something called language modeling, something like query likelihood, and the expansion models via relevance models. And you'll see these acronyms throughout the presentation here. DataMed, on the other hand, is using Elasticsearch based on Lucene, very, very popular open source search engine, increasingly used for research, but has its foundations in a different class of models called vector space models. And Okapi BM25, which kind of bridges a gap there, is the default today in Elasticsearch. We hit an interesting point, and if anybody's interested in talking about this, I'm interested in talking about this, that the language modeling implementation in Lucene is actually incomplete. So we had set our direction towards relevance models in our initial proposal, but found that, in fact, that relevance models weren't going to work well with Lucene as it is right now. So since there's no built-in expansion support in Lucene or in Elasticsearch, we looked at a very, very old method, the Rocchio method. The good news is, both from Indri and Lucene and in the probabilistic or the vector space models, is that if you have tuned models, they tend to perform comparably well. So familiar evaluation process. We've got the index test collection data from BioCaddy. We run our queries. We exhaustively sweep model parameters. One difference when you see the numbers that I'll report here is that we went with shortened versions of the queries, figuring that the long queries in the evaluation, in the test collection, were actually unrealistic for real user queries. So we went through a process of reducing those. We do have data for both runs, both shortened and the original queries. So we calculate our target metrics. We do leave one out cross-validation and kind of a paired t-test for testing the differences between the models. I think one difference between the works that's already been reported here this morning is we wanted to see the differences between the expansion models and the baseline models, both in dataset and non-dataset retrieval, and we wanted to do that somewhat controlled, where we're executing the exact same models with the same assumptions against several different test collections. So we've got the 2016 BioCaddy data. We limited ourselves to the test queries because of concerns about the relevance judgment depth in the training queries. And then we used the OHSU, kind of a very old Medline document title abstract collection, and then the Trek Genomics 2006 collection. So probably aside from the number of documents per collection, they have different characteristics: full text, document title, abstract, metadata, and then the number of queries is pretty important here as well. I'm going to report the non-inferred NDCG and map. I actually have some questions for Kirk and the team about calculating the inferred values here that I hope to address while in town. So, ugly table data for a couple of slides here, but this is using Indri, using language modeling, using relevance model expansion on the OSAMED, I call it, OHSU data and the Trek data, comparing the standard expansion, meaning using the local data set, with PubMed expansion with a standard query likelihood baseline, all through cross-validation. And the short of this slide is that it seems to work pretty well for the OSAMED collection. So title abstract, we see across the board improvements, statistically significant improvements. Again, whether that's the users can notice or not is potentially in question. Genomics is the queries we found were a lot closer to the BioCaddy queries. So we see maybe a less convincing role for expansion within the Trek Genomics collection. So the BioCaddy evaluation, and these repeat the results effectively what we did with the challenge, just without working with the complete test collection, is we see maybe some improvement at the higher ranks, and maybe some improvements at the lower ranks with the PubMed expansion. But there's not an overwhelming message here that expansion is going to do wonders for BioCaddy, at least with the assumptions that we've run with. So we looked in depth here to see, well, how does the performance of the individual queries change when we expand? This is a kind of complicated box plot, but basically looking at the change in performance of NDCG as you expand or don't expand. And things below the line are things that are at risk of reducing in performance, and things above the line increase in performance. And so we see higher risk with expansion, at least with these 15 queries. And this, I think, reinforces a comment made by that selective or adaptive expansion would be maybe the next step if BioCaddy is to look at expansion integration in the primary search engine. And we did a little work in this with trying to predict when to do expansion, but it was outside of our kind of core scope, so we dropped it to move on to the implementation. So even though the results are weak, we still think that expansion is probably a promising option for DataMed. Maybe we need a different external collection. Maybe we need to pay attention to field weighting. Maybe we need to do selective or adaptive expansion. With our concerns around Lucene support for language modeling, we went with Rokio expansion using BM25 scoring, and this has been maybe a little controversy there, but it's kind of a proven method over time. And so we have in a toolkit that we use for our own research for Lucene, really just for evaluation purposes, we've built a Rokio expansion module, and then we built a plugin for Elasticsearch. So a less rosy picture. So this is looking at BioCaddy's, the same test collection, but now using Lucene BM25 compared to Rokio expansion. We see even maybe there's no significant loss in performance, but we don't see real gains. And throughout these slides, I've thrown in stemming as an option. This is just a pre-processing step that often works in retrieval, and it seems to be somewhat effective with the BioCaddy collection. It's outside the core of expansion models, but we've seen it both within Indri and with Lucene that either Krobitz or snowball stemming has potential for some impact. The main pilot outputs are, for us, we've got the results, or actually we've got the comparative evaluation process that we used in the GitHub repository. This is specific to the BioCaddy, OSIMED, genomics collections, the scripts that we use to actually do the runs with Indri and with Lucene to produce the results. We have the results and data available, but we're still trying to figure out how to provide those from a data sharing standpoint. It's maybe not suitable for GitHub. We have a framework for experimental evaluation for Indri and Lucene that's freely available for use, so this would support cross-validation and parameter estimation using the Lucene models. And then we've got a prototype Elasticsearch plugin with the Rokio expansion, and we're considering working towards a paper here, not a software output, but a publication output for either ECIR or SIG-IR in the coming year. Just a quick example of the Rokio expansion module in Elasticsearch. So this is, for those of you working with Elasticsearch, you just install the plugin, you get a new expand endpoint, and we could really implement almost any expansion model under this. This just shows how to do it with Rokio. And you've got optional parameters both for the Rokio model and for the underlying BM25 model. And one caveat is, so term weighting in Elasticsearch was actually not as clear as it could be to me. So we ended up using what's called a query string query that allows you to pass through weighted terms to Lucene and Lucene's native language. So this is an example of what would be Lucene weighting with the carets. So I think maybe very similar results. The expansion results are inconclusive. Models that have proven to be very effective in general for a lot of collections aren't here. We still have some open questions about the test collection. So the small number of queries obviously affects any sort of statistical comparison, but also the judgment depth between the training and test data raise some questions as to whether those were really comparable, in particular when trying to train parameters. While Elasticsearch isn't well suited for evaluation, fortunately it's built on Lucene, and Lucene is something that we can do pretty good. And when I say evaluation, I mean this sort of comparative evaluation using parameter sweeps and cross-validation. But leucine has worked pretty well for this. So doing evaluation on top of leucine, it seems fairly effective that you can translate that into Elasticsearch down the line. And I think the same conclusion is that maybe a good next step would be to consider the selective or adaptive expansion models to predict when to expand, or looking at alternative collections or subsets of PubMed. So this is just some references from the progress report, and I don't have a clock in front of me. Hopefully we're okay, but thank you, and I'd like to say thanks for this opportunity. It was not only a lot of fun, but it was a great chance for us to really dig into the BioCaddy and DataMed system and to understand this problem a lot more. So thank you.